Guys, this is chapter 9, Quadratics 9.2, solving quadratics equations by graphing. All right, our goal is to be able to solve quadratic equations using a table of values and to find the roots of a quadratic. Sometimes we call roots solutions. So far, we've learned how to solve quadratic equations by factoring, if you remember the last chapter, but we can also use graphing to solve a quadratic equation. All right, recall that a quadratic equation is an equation that can be written in standard form ax squared plus bx plus c equals 0. The solutions or roots of an equation ax squared plus x plus c equals 0 are the x-intercepts of the graph. All right, so for in this example, if they graph this one, the x-intercepts are where it crosses the x-axis. Right, bear with me here, my stylus broke, so my lines won't be as straight as they normally are. But this crosses the x-axis right there at the point 3, 0, and right here at the point negative 2, 0. And if you were to factor this, that's exactly what you would get. All right, here's some kind of a general rule of thumb. One real solution is where, I mentioned this before we went on break, but where our parabola, if it comes down in the vertex, the lowest or highest point of that touches in exactly one spot on the x-axis, then there's only one real solution. Okay, that'd be like when we factored and we had x minus 2 times the quantity x minus 2. They're the same thing. You could solve that and get the point 0, 2 for both. When there's two real solutions, that's like that last one I just showed you, where it's going to cross the x-axis twice, here and here. And then sometimes there's no real solution, and that's like this last one where it does not cross the x-axis at all. It starts, or it comes down and goes back up before it touches that axis, or it's maybe even below. We do the same thing, goes down and back up. All right. Next slide here says, how many zeros does each function have? What are the zeros of the equations? Again, sometimes zeros we call roots. So if you might hear me say that interchangeably. This one, if I call this maybe number 1, this graph, this has 1 0 or 1 solution, and it's going to be the point negative 3 0 right there. And this next one has 2 solutions. If I call this number 2 has 2 solutions right there and right there. We have the point negative 2 0, and the other one is 3 0. All right, so let's solve these. We're going to solve it by graphing. Again, bear with me, my stylus is not currently working. But if we look at number 1, this equation, our a, b, and c is going to be 1, 4, and negative 5. Okay. You always want to double check that it's in the right order, and since our x squared term is first, followed by our x, followed by our constant, we know it is. This one's going to open up. Our a term is positive. All right. The axis of symmetry is the line x equals negative b over 2a. So on this one, the opposite of our b is negative 4 over 2 times 1. 2 times our a is just 2. Negative 2 or negative 4 divided by 2 is negative 2. So we have an axis of symmetry, x equals negative 2. Right? And if I were to even draw that dotted line like this, each side of our parabola should be cut exactly down the middle of that dotted line. All right, to find the vertex, we're going to plug in this negative 2 into our original equation, which was x squared plus 4x minus 5 equals 0. X squared plus 4x minus 5 equals 0. And instead of writing x, I'm going to leave open parentheses. And what we found with our axis of symmetry in the last step, that's what we're going to plug in. And if you remember, we found that x equals negative 2. I might even switch colors to show you that here. So we have negative 2 squared plus 4 times negative 2 minus 5 equals 0. And I'm going to plug that into my calculator. So parentheses negative 2 squared plus parentheses, oops, plus 4 parentheses, negative 2 minus 5, enter. And when I do that on this one, I get the value of negative 9. Okay, and that's my y value. So y equals negative 9. The vertex, however, is going to be an ordered pair where the x is from what we found in the axis of symmetry, negative 2, and then the y is that negative 9. Oops, yeah, negative 9 for both of those. I'm sorry. Negative 9. So again, if I were to graph that over on my graph here, negative 2, negative 9 is way down here. All right, next thing I want to do is fill out our table. And if you remember, our vertex from this last step was the point negative 2, negative 9. So let's go 2 smaller than negative 2, which would be negative 3 and negative 4, and 2 larger than negative 2, which is negative 1 and 0. Now, since this is symmetric, we only have to plug in 1 on either side, and we can fill in the rest of that table. What I mean is if you go back to your calculator where you just did the, where you plugged in negative 2 for your x, I'm going to now maybe plug in negative 1. So switch that to negative 2s and write negative 1, and it goes a lot faster, and it gives you negative 8. It's faster because it should already be in your calculator. You just hit the up button, and it gives you the previous entry. All right, next one I want to try is 0. So instead of plugging in negative 1 now, I'm going to switch that all to 0. And like that, and I think it gives me a negative 5. So here and here. Notice I filled in the other spots too, since this is symmetric. We're going 1 away on each side of our original. So we have negative 8s for both negative 3 and negative 1, and negative 5s for both the negative 4 and the 0x entry. All right, so if I graph this, we have negative 1, negative 8, negative 3, negative 8, and then negative 4 was negative 5, and 0 was negative 5. So we get a parabola. It looks like this. Oops, kind of missed on that, but you can see how that dotted line I drew earlier does cut this one exactly in half. This one has a minimum value since it opens up. Oops, I think they want us to write that in, minimum. And we don't have to worry about the value section. The y-intercept, this is going to be when x equals 0, what is y? And sometimes if you graph it, or if you use your table, you'll even see this. Ours is the point 0, negative 5, because we have what y equals when x is 0. So our y-intercept is 0, negative 5. Right? And then the zeros of this one, if I go back to my graph, notice I kind of stopped before I got there. So what I want to do, I'll erase that, is I want to erase these a little bit, and I want to figure out if I kept going on my table, would I be able to figure out what the zeros are? Okay, so let me get back to my pen. And how about I put in a 1? Maybe that would do it. Okay, and if you hit the up button back in your calculator, I think you can go ahead, instead of, I think we had 0 left. If we switch that to be a 1, good, yeah, we do get 0. And 1 the other way, if I put a negative 5 right there, and I'm kind of writing over that, but I also get a 0 for that y. So my zeros would be 1, 0, I'll keep that going, and I think it was negative 5, 0. So I didn't draw this one the best, but it would be coming up like that. And that's where it crosses our x-axis. So it was the points negative 5, 0, and the point 1, 0. Those are the zeros of this equation. The domain and range, the domain is always going to be negative infinity to positive infinity, and those get parentheses. The range, since ours starts, our lowest y value is down here at negative 9, ours is going to be from negative 9 with a bracket to infinity with the parentheses. Okay, and that is that problem. Let's try another one. This is example 2. Using this equation here, our a, b's, and c's are going to be -1, 2, and notice it doesn't equal 0, so we need to probably move that over. I probably should have done this at the beginning, but that would give us just -x² plus 2x minus 1, then it would equal 0. So our c is going to be -1, not +1. Excuse me. This one opens down, since our a is negative. Its axis of symmetry is x equals -b over 2a. And our b was 2, so we want -2 over 2 times -1. That's going to be -2 over -2, which is +1. And so we have the equation x equals 1 for our axis of symmetry. Again, I could draw that dotted line, that vertical line at 1, and that's where our parabola should fold over itself symmetrically. The vertex of this one, if we plug in 1 for all the x's, let's see, -x². I might have to go back and forth here for a second to get this down. -x² plus 2x minus 1 equals 0. Plus 2x minus 1 equals 0. Let's see, this should be a plus sign. There we go. And I'm going to plug in 1 from the axis of symmetry. So it will look like this. I'm going to leave it blank for a second. That really helps me out. I don't know if it does you or not. Minus 1 equals 0. And in that spot, I'm going to put 1s. Okay, let's try to do this one in our head. 1 squared is 1, and then we have to make it negative from the negative out front. Plus 2 times 1 is 2, minus 1. And this equals 0. Let's see, -1 plus 2 1 minus 1 is 0. It does equal 0. So we have 0 for our y value. So the vertex, again, is going to be the point 1, 0, 1 from the x in our axis of symmetry, 0 for the y value that we just found. All right, this one, if we plug in that point, 1, 0, to the middle of our table, let's go 2 less than 1, so we're going to have 0 and -1, and 2 greater than 1, 2 and 3, and we're going to find the y values of each of those. Okay, so let's see, we have the equation negative parentheses. I'm just going to start by plugging in 1 squared plus 2. I'm doing this in my calculator right now, so bear with me. Parentheses 1 minus 1, enter. Oops, minus 1, delete, enter. And we do get a 0. All right, that's wonderful. Now I'm just going to go up to 2, and instead of 1s, I'm going to plug in 2s in place of the x spot there, and I get -1. And since that was 1 greater than 1, if we go 1 less than 1 to the 0 spot of our x, we would also get a -1 for the y. Oops. -1 for the y. Let me now change that to be 3. So change the x value to be a 3, and that's a -4. And up here would also be -4 since those are symmetric. All right, let's graph it now. On our graph, we start with the point 1, 0, which is right there. Again, I don't have my stylus, so these aren't as straight as they normally are. 0, -1, and 2, -1. 0, -1, 2, -1 are going to be those points. And then -1, -4. Whoa. 1, oops, -4. And 2, -4. Nope, 3, -4. Sorry, 3, -4. I'm having trouble here. And it's going to open down, which is what we said earlier. Kind of like that. All right. Once we have that graph, we can see just by looking at it that it's only going to cross our x-axis in exactly one spot. Okay, so I'm getting a little bit ahead of myself. That's going to be our zeros, but keep that in mind. This one has a maximum value. We don't need to know what that value is. And the y-intercept of this one, again, we're looking at our table, seeing if there's a spot where x equals 0, and there is. So this is going to be the point 0, -1. That's where it crosses the y-axis. And look, it does right here. 0. Ooh, don't know what happened there. 0, -1 is this point, and so that is true. Right, then remember I said the zeros, I want to keep that in mind, is where it crosses the x-axis. Looking at ours, it crosses here at the point 1, 0. Okay, and so that's the solution, or the zeros, roots. You'll hear me say all those things. 0.10. Okay. When there is only one point or 1, 0, that's always going to be the vertex. All right, so if there's ever one that has 2 points or no points, then that's not going to be the vertex. But in quadratics, where there's only one solution, the point that is the vertex. So maybe keep that in the back of your mind. The domain, like always, is -infinity to infinity. Okay, and then the range, remember this one goes down. So we're going to start at -infinity and we go up to 0. The y value is 0 when we are at its highest point. So from -infinity to 0, infinities get parentheses, zeros get brackets, and that is where we'll stop.